The new one.
Yes, I have this. I got 12. Yes. Thank you.
Okay, gotcha. Okay, we're on, right? Right. So the first question is, as usual, are there any questions? So everybody's up to date? Where we ended was we talked in detail about the Erlang B formula and about measures of performance like offered load and carried load. And then we looked at some numerical examples. And I gave you a recursive relationship that allows you to compute the Erlang B. Okay, so if everybody's okay on that, the next thing to do is to move to the next model, which is the Erlang C, which starts in the book on page 90. Okay, so here's the model that we're talking about. We have Poisson arrivals with rate lambda, and we have exponential service times with average service time tau. So we have an offered load of A equals lambda times tau Erlangs, and then we have an infinite number of waiting positions, and then we have a bunch of servers. So whereas previously we had blocked customers cleared, meaning that the customers who arrive and find all the servers busy overflow and are cleared from the system, now we have what's called blocked customers delayed, which means that if a customer finds all the servers busy, then he waits in a queue, and the length of time he waits is whatever is required. He waits as long as necessary for service. So this is the classic queuing model. And in fact, there's a notation which was originated by Kendall in the 50s. And his notation goes something like this: A/B/C, where A corresponds to the arrival process, B is the service process, C is the number of servers, and the assumption here is that it's a queuing model. That is, that the blocked customers are delayed or wait in a queue. So that's presumed when you use this notation. Now, the model that we'll be looking at today then, based on that, is what's called MMS. This M stands for Markov, means Poisson input, memoryless input, exponential inter-arrival times, just like before. So we have PASTA. This stands for exponential service times. Now this is different. When we looked at the blocked customers cleared model, we did not have to have exponential service times. We had that amazing theorem, the insensitivity theorem, that said that although the exponential service times assumption is sufficient for the rate up equals rate down, it's not necessary. It's usually necessary, but not necessary in every case. This is a case where it's necessary. It was not necessary before. So now we have exponential service times. We also allow the number of servers to be arbitrary, S, any number of servers. So as before, we want to write rate up equals rate down. So now, here's rate up equals rate down. So as before, if we're in state J and the arrivals are occurring at rate lambda, then by PASTA, the PJs and the PIJs are the same. And so this is the rate up from state J. So that's just the same as before. However, now we have two different cases for the rate down. If the state J, J plus 1 in this case, if J plus 1 is less, let me put it this way. If the state of the system is such that there is no one waiting in the queue, then everybody present is being served. And therefore, the service completion rate would be just as before. Namely, it would be 1 over tau per customer being served. So in this particular case, if I'm in state j plus 1, then the service completion rate would be j plus 1 over tau. So this is valid as long as j is less than s. Okay, now if I'm in a state j greater than or equal to s, because when j is less than s, the highest it can be is s minus 1, and so this then would be state s. Okay, so when j is greater than or equal to s, that means that that all of the customers in the system more than j are waiting in the queue. And therefore, those customers who are waiting in the queue, their service completion rate is 0 because they're not being served, they're waiting. And so therefore, the service completion rate for j greater than or equal to s is s over tau. Okay? Excuse me, if the j plus 1 is s or more, then that means that s customers are in service and the remaining customers are on the queue. And if s customers are in service, then the service completion rate is 1 over tau times s, the number of customers in service. In fact, where I am in the textbook is I'm on page 90. There, things are written a little bit differently, but basically it's the same thing. So now I have rate up equals rate down, so I have two differences. One is that the rate down part of the equations change, and the other is that there's an infinite number of states. So now I can solve these equations. I mean, I could write them out. Lambda p0 is equal to 1 over tau p1. Lambda p1 is equal to 2 over tau p2. Lambda ps minus 1 is equal to s over tau ps. And then everything after that is of the form lambda pj is equal to s over tau pj plus 1. So I solved the equation just as I did before. So what I get is P1 is equal to lambda times tau, which is A, P0. And then I get that P2 is equal to A over 2 times P1, or in other words, A squared over 2 factorial P0, and so on. So what you see is that Pj is equal to a to the j over j factorial p0 as long as j is less than s. So if that's for j equals 1, 2, and so forth, up to s minus 1, say. So that's what I get when I solve these equations here. Okay, now, how about when j runs from s to infinity? Now the equations are going to look a little bit different. Let's see, I'll write them here. In the case of s, I'm going to find that p sub s is equal to a over s ps minus 1, which is equal to a over s a to the s minus 1 over s minus 1 factorial p0. And then I'll find that ps plus 1 is equal to a over s ps, which is equal to a over s a to the s over s factorial p0, and so on. So what I'm going to get is that pj is equal to, all right, now if I write this thing out, it's going to turn out to be equal to a to the j over s factorial times s to the j minus s p0 as j runs from s to infinity. Of course, I could use either of these forms when j is equal to s, because if I plug in j equals s here, this and this turn out to be the same thing. In the book, these are equations 4.3 and 4.4. Okay, so that's the solution of the rate up equals rate down equations. This is just algebra. Now, the next question is, how do I find P0? So previously, the way I found P0 was I required all the probabilities to sum to 1. So the same thing will be true here. So that means that I can write it like this. P0 times the sum. All right, now first we'll look at these guys here, and I'll write this as the sum of a to the k over k factorial as k runs from 0 to s minus 1. Okay, that takes care of adding up all probabilities of this form, including the 0th one, plus the sum as k runs from s to infinity of a to the k over s factorial s to the k minus s. And all of that has to add up to 1. So that means that P0 is the reciprocal of the thing in parentheses. However, previously, what we had was the sum from 0 to s of terms that looked like that. And in that case, there was no problem about convergence of the series. But over here, we have an infinite series. So that means that this series might diverge. So let me write out the terms what this series is. Okay, so if I write this out, let's see, I could, the first term here would be a to the s over s factorial. So I'm going to factor out an a to the s here. In fact, I'll write this as a to the k minus s, and then put an a to the s over here. So when I factor out the a to the s over s factorial, that's those terms right there, then when k runs from s to infinity, I have a to the 0 over s to the 0 plus a to the 1 over s to the 1 and so forth. And in fact, what that's going to be is the summation of a over s to the k as k runs from 0 to infinity. Maybe I should use a different symbol like I so I don't get confused with that k. Let me write it like that. A to the s, a over s to the I, as I runs from 0 to infinity. Okay, now as everybody knows, this piece right here, this is a geometric series. And so it has two answers. The geometric series converges to 1 over 1 minus the thing being raised to the power if the absolute value of that thing being raised to the power is less than 1. We don't have to worry about absolute values here because a and s are non-negative numbers. So if a over s is less than 1, then that series is 1 over 1 minus a over s. So that's what I get if a over s is less than 1, or equivalently, if a is less than s. On the other hand, if a over s is not less than 1, then that series diverges, so I'll just write infinity for a greater than or equal to s. Okay, so now let me go back over to here and write down what my answers are. What I have is that Pj is equal to a to the j over j factorial P0 if j is less than s, and it's equal to a to the j over s factorial s to the j minus s P0 if j is greater than or equal to s, and P0 is equal to two forms. In the first case, in which I have convergence, in which this infinite series converges, then this term right over here is equal to a to the s over s factorial times 1 over 1 minus a over s. So in other words, P0 is the reciprocal of this sum, the sum as k runs from 0 to s minus 1 of a to the k over k factorial plus a to the s over s factorial times that, a to the s over s factorial divided by 1 minus a over s. And that's what P0 is if a is less than s. Now, if a is not less than s, then this series diverges to infinity. And so formally what we could say is that P0 is 1 over infinity, or 0. Now, this makes perfect sense, as we'll see in a moment, when I interpret what this condition right over here means. That is the condition that a must be less than s. Okay, but for right now, what we have is we have a formulas for calculating these state probabilities, because I can calculate each pj from this formula, and I can calculate p0 from this formula. Now, if a is less than s, then we have a proper distribution in which all the probabilities are positive and their sum adds up to 1. And if a is not less than s, then according to this, all the probabilities are 0, because each of these is multiplied by p0, which means that I could interpret this by saying that the probabilities are 0 for every finite state, and the probability of being in an infinite state then would be 1 if I want the probabilities to sum to 1. So in this case, what I'll say is that the probability of state infinity is 1, whatever that means. Okay, now the next question is, what do we mean when we say a is less than s? Okay, because obviously a is less than s is the important case, because that's the case where you get a legitimate probability distribution. If that condition isn't met, then what that says is that there is no equilibrium distribution, because, or no proper one, because the probability of being in any finite state is 0. Okay, so what does it mean then? If we say that a is less than s, what you're saying is that lambda times tau is less than s, which means you're saying that lambda is less than s over tau. Now, looked at it from this point of view, this makes perfect sense, because it says that in order to have a necessary condition, and a sufficient condition, in order to have an equilibrium distribution, is that the arrival rate must be less than the maximum average service completion rate. Because remember, when we wrote the equations, this piece right here, that's the rate down when you're in a queuing state, when all the servers are busy. So what this says is that if the arrival rate is less than the maximum rate at which the server spits these guys out, because remember, when all servers are busy, then there's an output process. Here it is. In fact, there's an output process whether all servers are busy or not. But the rate at which customers leave the system is given by that or that. And the highest possible service completion rate that you can get, aggregate service completion rate, is s over tau. So s over tau is the maximum long-run rate at which the servers can do this work and get the customers out of the system. So what this says is that in order to have an equilibrium solution, the rate at which the customers arrive must be less than the maximum rate at which the servers can get rid of them. If not, then customers are arriving faster than the servers can handle them, and that means that over the long term, the queue length is going to build beyond any finite bound, which means that for every finite state, the probability of being in that state will be 0, which means that for the infinite state, the probability that the queue length is infinite must be 100%. All right, so one difference between this model, two differences now between this model and the other model are, first of all, it turns out that we don't have this amazing theorem that says that these answers are independent or insensitive to the service time distribution. In this case, we must have exponential service times. And the second thing is that there's a critical value of the offered load. Namely, the offered load must be less than the number of servers in order for there to be an equilibrium solution. And if it's not, then mathematically there is no equilibrium solution. From a practical point of view, what it means is that the queue lengths are going to be very large, and you're going to see a lot of congestion. So as a practical matter, you want to keep the offered load in Erlangs below the number of servers. Of course, remember that this would be the offered load. Now, the carried load, well, this would say that the offered load must be less than, let me prove something first, and then I'll go back to the statement and clarify what this means when I talk about loads. Any questions up to this point? Okay, so far this is just algebra. Is there a question there? Okay. So far this is just algebra, but a little bit different from before. Now, before, we wanted to calculate the probability of blocking, which was also the probability of loss. So for the Erlang B, we calculated the probability that all servers are busy. But now, I'm going to calculate the Erlang C. So this is another formula. Let me give myself more room here. Another formula analogous to the Erlang B. So it's defined to be the probability that the system is in the blocking state. So previously, the blocking state was only state S because you couldn't have any more customers present. There was no room for queuing. But now, you can have any number of customers in the queue. So the probability that all servers are busy is the probability that the number of customers present is S, or S plus 1, or S plus 2, and so forth. And by pasta, this is also the fraction of arriving customers who find all servers busy. So therefore, it's the fraction of customers who do not get service immediately. So obviously, this is an important performance measure. So analogous to the Erlang B formula, we have the Erlang C formula. So when I sum this series, I'm going to get an answer. And in Europe, this is sometimes called Erlang's second formula, as the Erlang B was Erlang's first. So there's the B and C, or the first and second. Actually, there's another formula implied by the initials B and C, which is the Erlang A formula. That turns out to be less useful. I'll talk about that later. Okay, so now I want to figure out what the Erlang C value is. Well, I've already figured this out because I've already computed this sum, and I saw that when I computed the sum, it was equal to that times P0. Remember, that's how we got this, is we added up all of those probabilities from S to infinity, and this was the term that corresponded to it. Except that it had the P0 in front of it. That's where it came from. So this thing is equal to a to the s over s factorial times 1 minus a over s times P0, or in other words, a to the s over s factorial 1 minus a over s divided by the sum as k runs from 0 to s minus 1 of a to the k over k factorial plus the same term as in the numerator, a to the s over s factorial 1 minus a over s. And of course, that assumes that that infinite series converges. So this is the answer if a is less than s. So that's the Erlang C formula. Okay, that's given in the book, equation 4.8. And if you wanted to, you could say that the Erlang C value is equal to 1 if a is not less than s. Meaning that if a is not less than s, the probability of blocking is 100% because the queue length is infinite. Okay, so here's a formula now which is analogous to the Erlang B, just as useful. and it calculates the fraction of arriving customers in a system in which the block customers wait as long as necessary for service, the fraction of arriving customers who, when they arrive, find all the servers busy and therefore have to wait in the queue and are denied immediate service. Now, let's calculate the carried load. Do that over here. Remember the definition of carried load. Carried load is equal to, was defined to be the average number of busy servers. So it was the sum of JPJ, where J is less than S, plus the sum of SPJ, where J is greater than or equal to S. This is the average number of busy servers. When I'm in a state J, where J is less than S, then all the customers present are holding servers. And when I'm in a state J, where J is greater than S, then S of the customers are holding servers, and the rest of them are in the queue. So now, since I have the state probabilities, which of course I just erased, that's an example of good pedagogy, right? You erase something and then you use it immediately after erasing it. If I took those probabilities and plugged them in here, I would be able to sum this series, hopefully. And the answer is, if you do that, and it's just an algebraic exercise, so I'll write after algebra, the answer turns out to be exactly what you would expect. At least as soon as I write it down, you'll say, yeah, that's what I expected. It turns out to be exactly A, which means the carried load is equal to the offered load. But that makes sense, because if everybody who arrives gets served, then the total amount of work that's brought into the system is the total amount of work that's actually handled by the system. So that means if I tell you that I have a system with 10 servers and I offer 8.2 Erlangs, then the average number of busy servers is 8.2, and I carry 8.2 Erlangs, which means that the utilization of my servers, rho, which by definition is the carried load divided by the number of servers, well, that's what it is. That's the same as the offered load divided by the number of servers. So that makes everything easy, because now I can talk directly in terms of server utilization. With the Erlang B, I couldn't do that. So this is a nice simplification. And this is just an arithmetic exercise to prove that from this definition, carried load and offered load are equal. OK, so now the next thing I want to know is, how am I going to calculate this Erlang C value? So, of course, I could calculate it directly from its formula. But that's messy. Certainly it's messy to do by hand, because you've got these powers and factorials. So if the Erlang B was hard to do, well, the Erlang C is worse. Although, of course, you could write a computer program to do this. And if you did it directly, you wouldn't, you'd run into trouble when the values of A and S get too large. But just like there was a recursive formula for the Erlang B, now I can relate the Erlang B to the Erlang C. So this is left as an exercise, exercise 16 on page 92. And the exercise is only algebra. That is, I'll just write down the answer on the right-hand side, and the way you prove it is by substitution and cancellation. So the Erlang C is equal to S times the Erlang B divided by S minus A times 1 minus B of S and A. So that's really very nice. That's really neat, because what this says is you have a recurrence relationship that allows you to calculate the Erlang B very easily. So if you have such a program, then you can calculate the Erlang C with just one more instruction. because all you need to do is each time you calculate the Erlang B, you just substitute it in this formula. There's no problem, no numerical problems here because the Erlang B is always a number that lies between 0 and 1, so this is a very simple piece of arithmetic. So this is very nice to know. That can be written also if I divide through by S. I could write this as B of SA divided by 1 minus A over S times 1 minus B of SA. And of course, A over S is the utilization. So I can write this as B of SA divided by 1 minus rho times 1 minus B of SA. A over S is the utilization because of this statement right here. Now, one minor problem with this is that remember that the Erlang B is valid for any value of A, whereas the Erlang C is valid only for A less than S, because when A is greater than S, the Erlang C should be replaced by 1. So you've got to be careful when you compute this. Although you could just take the viewpoint that if you compute it and it turns out to be a number greater than 1, then you replace it by 1. Another way to look at it is this. In fact, if I look at it here, I can say, well, why don't I define rho this way? I'll define rho to be equal to A over S if A is less than S, and 1 if A is not less than S. In other words, the utilization of the servers is 100% when the offered load is greater than the number of servers. And that's obvious because when the offered load is greater than the number of servers, then with probability 1, you have an infinite queue. And so if the queue length is infinite, then the servers are always busy, so the average number of busy servers is equal to S. So the utilization is 1. And in fact, then each server is carrying, if A is less than S, on average, each server is carrying A over S Erlangs. And if A is not less than S, then each server is carrying 1 Erlang. And a server that carries 1 Erlang is busy 100% of the time. That's what 1 Erlang of traffic is. 1 Erlang of carried traffic is the amount of traffic that keeps one server busy all the time, 100% of the time. Okay, so with that, if I interpret rho that way, then I can see that when rho is less than 1, then this is the same as this. And when rho is when A is greater than S, so that rho is equal to 1, then what happens is the denominator simply becomes the Erlang B, which cancels with itself and gives you the Erlang C value as 1. So then this formula captures the whole thing. Now, with the Erlang B, you had curves that looked like this. Here's the offered load. Here's the Erlang B. Here's the value 1. For one server, the curve looked like that, while it was asymptotic to 1. And for 2 servers, like that, and 3 servers, and so forth. The point is that as the offered load gets bigger, the probability of blocking approaches 1, but never reaches it. It's only asymptotic to 1. But in the Erlang C, the situation is a little bit different. There's the offered load. Here's the Erlang C value. Here's the value 1. Now, suppose that I had 1 server. If I had 1 server, then as the offered load gets bigger, then the probability of blocking gets higher until A reaches the value 1. And then the Erlang C reaches the value 1. So the curve looks like this and then stays at 1. For the curve S equals 2, when A reaches the value 2, the curve reaches the value 1, is not asymptotic to it, and then stays 1 forever, and so on. So now your family of curves looks a little bit different. And these are plotted in the book, I think page 320 or something like that, back of the book, right next to the Erlang B curves. Notice that from this statement right here, there's some interesting things here. It's amazing sometimes the way these things work out. First of all, for some strange reason, notice that the value that's right here in the denominator, this piece, is in fact the same formula as was calculated earlier for the carried load in an Erlang B system. So this thing then is a number of Erlangs which cannot be S or more, because if I have an Erlang loss system, then the carried load is always less than the number of servers in the system, which is S. So if I have an S server Erlang loss system, the carried load must always be less than the number of servers. So therefore, the denominator can never go negative. Furthermore, note that the numerator, this can be written as S divided by, well, let me say it this way. I could factor this term out. And so I see that the Erlang C is something times the Erlang B. And that something times is S divided by S minus something. So the denominator is smaller than the numerator. So therefore, the multiplying factor is greater than 1. So that means that Erlang C is always greater than Erlang B. Okay, so we know immediately that for any A and S, the Erlang C is greater than the Erlang B. Unless of course A equals 0, and then I guess the probability of blocking is 0 and they're both the same. But in any meaningful case, the Erlang C is always greater than the Erlang B. Question is how much? Now we can get some numbers out of this. So what I'd like to do is just make up some numbers, and I have my little handy-dandy computer here, and calculate the Erlang C for some values, whatever it is you want to pick, just to get an idea as to what these numbers are. Now, the way I do it is I calculate the Erlang B along the way, because I calculate the Erlang C from the Erlang B. So if I'm going to get the Erlang B anyhow, so that we can immediately then compare Erlang B and Erlang C for same value of offered load and number of servers. Okay, so why don't you give me some values, and then I will give you the numbers. Okay, what value of S do you want to use? How many trunks, servers? 15? Okay, so take S is equal to 15. What about A? What's the offered load? 10. Okay, so that's going to give me a utilization in the Erlang C system of about 67%, 2/3. Okay, so that means that I'm going to put in S equals 10. I'll put in A equals 15. And it tells me that the Erlang B value, so the Erlang B of 1510 is equal to 0.41. I'll get it down to 2 decimals. So 41% of the customers are blocked. The carried load in this case for the Erlang C, for Erlang B, turns out to be 8.85 Erlangs. And that's what you get when you realize that what you're doing is you're offering 10 Erlangs, and 41% of those are going to be blocked. Right? No, wait a minute. What? Just flip the numbers.
You did S to the 10 and A to the 15. That's okay.
Okay, wait a minute. Yeah, okay, right. So we're okay. Everything I wrote down on the board is right. No.
Not the top portion. S is equal to 10. That's what you did.
Oh, S is equal to 10. You mean I put in 10?
Yeah, you put it in.
All right, okay. I put in 10, and then I put in A equals 15. Okay, that's why things aren't working. Okay, so this is the probability of blocking, and this is the correct carried load. But when I do the Erlang C now, the answer should turn out to be 100%. Okay, let's see. Okay, Erlang C, my program tells me is 1. So C of 1015 is equal to 1. That's because the offered load is greater than the number of servers. Okay, let's try another one. Suppose I took S is equal to 10 and A is equal to 8.5. 8. Let's not be fancy. So I have 10 servers, 8 Erlangs. Okay, wait a minute here. Okay, I'm going to put in S equals 10. I'm going to put in A equals 8. Press the button, and the Erlang B of 10 servers, 8 Erlangs, is equal to 12%. The carried load is equal to 7.03 Erlangs. The Erlang C for 10 servers, A Erlangs, is equal to 41%. And of course, the carried load is exactly equal to 8 Erlangs. All right, so here you see the difference between the two. 12% blocking, 41% blocking. But this means that 12% of the customers are lost. This means that 41% of the customers are delayed, but nobody is lost. Now, if I scaled things up, let's calculate the same thing. For instead of 10 servers and 8 Erlangs, I had 100 servers and 80 Erlangs. Okay, so I'm going to do B and C of 180. Now you should have much greater efficiency. So I'm going to put in S equals 100. I'll put in A equals 80. Of course, now it's got to iterate through this program 100 times. So it gives the Erlang B turns out to be equal to 0.004. The carried load, of course, turns out to be very close to 80 Erlangs, 79.68 Erlangs, which is what you would expect because you're offering 80 Erlangs and you're carrying 99.6% of them. The Erlang C is now 1%, actually 2%, 0.0196. So it's still fairly small, but of course it's much bigger than that. Any other particular, and of course it's much better than that. We went from here from 12% to 0.4%. Here you go from 41% to about 2%. But the utilization is the same in both cases. It's still, the carried load here is 80 Erlangs, which means the utilization is 80 over 100, or 80%. Over here, the utilization is also 80%. So knowing just the utilization doesn't by itself tell you very much. Any other examples you want to see? Can you think of any numbers, any particular strange number? This is all easy now. And you can see how useful this is. Of course, it's useful in the sense that it gives you the fraction of customers who have to wait, but it doesn't tell you how long they wait. So ordinarily, for systems in which no waiting is allowed, then the important performance measure is what fraction of the customers are denied service and what fraction of the customers are given service. That tells you what your system is doing. In a system in which queuing can occur, is allowed to occur, there's room for queuing, then the probability of waiting is not necessarily in itself important. But what may be more important is how long do you wait? If you have a high probability of waiting, but you wait for only a short time, then for all practical purposes, it may not make any difference. Okay, so that introduces a new wrinkle because everything up to this point has been easy in the sense that we've been talking only about discrete variable, namely the state of the system. State defined in terms of number. Okay, but now we're defining something new, which is time, and so that's going to add a complication. Okay on this? Of course, there's lots of ways you could make up homework exercises with this. But most of it's straightforward. Okay, so now let's look at the next section. Well, I'm going to skip the next section. I'm going to go to the section that begins on page 95. I'm going to talk about waiting times. Okay, so everything is simple, right? So now I'm going to let W equal the waiting time. And later I'm going to talk about R, which is the response time, which I'll define. So the waiting time is the time from the instant the customer arrives until he enters service. So with probability 1 minus the Erlang C, his waiting time is going to be 0. The response time, by definition, is the sum of the waiting time plus the service time. Okay, so let's talk about the waiting time first. What I want to calculate is the distribution function of the waiting time, which by definition is the probability that the waiting time is less than or equal to t for all t. But it's more convenient to calculate the probability that the waiting time is greater than t and subtract it from 1. Now, the probability that the waiting time is greater than t can be written as the probability that the waiting time is greater than 0 times the probability that the waiting time is greater than t given that the waiting time is greater than 0. This part we already know. That's the Erlang C value. So that means that my calculation is reduced to this part. This, of course, is independent of the order of service. I haven't mentioned whether the customers are served first come, first serve, last come, first serve, or what. So obviously it doesn't matter because the number of customers present doesn't depend on how you select them from the queue. Statistically, the customers are interchangeable. But if I want to calculate the probability that I wait beyond a certain length, then of course it's going to depend on whether when I arrive I'm served in front of the customers that are ahead of me, or I'm served behind the customers ahead of me, or something like that. I mean, I can be served in order of arrival. I could be served in reverse order of arrival. I could be served in random order, or there could be some kinds of priorities. Who knows? So first I'm going to do this for the simplest case. In fact, I'm only going to do it for the simplest case, which is service in order of arrival. But I'm going to do it differently from what's in the book. The way it's in the book is start with this, calculate this. Now what I'm going to do is, in fact, I'm going to calculate this, and then I'm going to deduce this part by recognizing that it must be this product. You can do it whichever way you want, but the second way seems to me to be a little bit more instructive. You always think that, however you want, whenever you write a book or paper, you always do something the way you think is best after a lot of thought, and then as soon as you see it in print, you know that there was really the other way you should have done it. Sort of one of those laws of research, I think. All right, so here's what I'm going to do. I'm going to calculate the probability that a customer, an arbitrary customer, waits longer than t. So, first of all, that's the sum of the probability that the arriving customer finds the system in state k times the probability of waiting greater than t, given that the number that he finds when he arrives is k, summed over all k. So this is just a theorem of total probability. Okay, the next step is be a little bit more precise here. First of all, I'm going to replace pi k by pk. That's by pasta. Okay, so this equal sign here is by pasta because the probability that the arriving customer finds k in front of him is equal to the probability that the outside observer sees k in front of him sees the system in state k because we have Poisson input. Okay, so that's that piece. And let's see, I'll write everything out in detail. So here's the probability of w greater than t given n is equal to k. And here we note that the k is really summed from s on up because this probability for any k less than s is 0. Because if he arrives and he finds less than s customers in the system, then that means when he arrives he finds an idle server, so his waiting time is going to be 0. So it won't be, so for any positive t, that's what I want to do. Okay, now I'll rewrite that as the sum. I'm going to write that as the probability of being in state s plus j times the probability that the waiting time is greater than t given that the number is equal to s plus j. And I'm going to sum as j runs from 0 to infinity. Okay, so when j is equal to 0, that means that the customer arrives and he finds all servers busy but nobody on the queue in front of him, and then he has to wait. Or he finds all servers busy and one in front of him, or two, and so forth. Okay, now, what is this piece right here? Well, these are just the state probabilities with the j that I wrote earlier replaced by s plus j. So in fact, this thing is now a to the s plus j divided by s factorial s to the j times p0. That's what we got when we solved the rate up equals rate down equations. So in fact, this is equation 4.4 in the book. That is, it's 4.4 is the one that says that that is equal to that. So now I'm going to take the a to the s over the s factorial outside and rewrite this as a to the s over s factorial times p0, that's this piece right here, times the sum as j runs from 0 to infinity. Okay, now what's left? I took the a to the s and the s factorial outside, so I have a to the j over s to the j, which is the same thing as a over s to the j. And I still have the probability of w greater than t, given that the arriving customer finds s plus j in front of him. Okay, now let's see. I think I'll go back up to here. So I'm going to continue around. I'm going to loop around. I'm going to write this as follows. I'm going to note that a over s is equal to rho, the server utilization. So this is going to be rho to the j. In fact, what I would like to do is I would like to put a 1 minus rho in here and a 1 minus rho out there. Okay, so continuing along, I'm going to write this as a over s, a to the s over s factorial times 1 minus rho times p0. So I divided by 1 minus rho, so now I'm going to multiply by 1 minus rho. So I have the summation as j runs from 0 to infinity of 1 minus rho, rho to the j, times the probability that w is greater than t, given number in the system is s plus j. Now, this piece right over here can be shown to be exactly equal to the Erlang C. In other words, if you go back and look at the formula for the Erlang C, well, that's what it is. So this act here is by 418, where the formula for the Erlang C is given. Now, it's interesting. This piece right here, well, I don't know what it means at the moment, but it's a geometric distribution. In other words, what we have here is a geometric distribution, in a sense, weighted by these probabilities. So it turns out that that actually can give some insight. Although, algebraically, what I'm going to do is I'm going to ignore this 1 minus rho. So the trick is that I have to calculate this piece here. Okay, so going back over to here, the probability of weighting greater than t is given by this. Here's the Erlang C right here. So that part is the probability of weighting at all, and this whole sum is the conditional probability of weighting greater than t, given that you have to weight it all. And notice that I haven't made any assumption yet about the order of service, about the Q discipline. But now I'm going to make an assumption about the Q discipline. So now I'm going to assume FIFO. And now, assuming FIFO, what I want to do is I want to calculate the probability of weighting greater than t, given that I find a Q of length j in front of me, knowing that those j customers are served before me, and anybody who arrives behind me is served after me. Okay, so here's the picture. Here are the servers. There are S servers, and here's the Q. And the Q is of length j. And here is U, the test customer. I want to calculate the probability that you wait longer than t, given that when you arrive, you find all servers busy and j other customers in front of you. So if j is 0, you still have to wait because you find all servers busy, but then you're at the head of the queue. So the obvious way to do this is to calculate the length of time that each customer on the queue spends at the head of the queue, and then take the j-fold convolution of that and then plug that into this formula. But actually, you can do it in a much quicker way if you take this viewpoint. Suppose I say that recognize that what happens here is that there are these departures. And if this is an interval of length t, let's say, then I will wait longer than t if the number of departures in length t is not enough to get me into the servers. So suppose that j were 0. If j is 0, then I will wait longer than t if the number of departures in its interval of length t is none. If j is 1, then I will wait longer than t if the number of departures is 0 or 1, and so forth. So what I want to do is I want to calculate the probability that during an interval of length t, I have j or less departures. Okay, so here's the interval of length t. Okay, the probability that I wait longer than t if I find all servers busy and j customers on the queue in front of me is equal to the probability that in this interval of length t, the number of departures is either 0 or 1 or 2 up to j. So I'm going to sum, as I runs from 0 to j, the probability that in the interval of length t, I have exactly I departures. Okay, so now the question reduces to, what's the probability that if all servers are continually busy between 0 and t, the number of customers that they spit out is exactly I. Okay, now let's take a look at the time from when the test customer arrives until the first departure. How long is that? Well, when he arrives, he finds a bunch of guys in service. There are S guys in service, and the length of time remaining in service for each of those guys is the same. It's exponential, they're independent, and the average value is tau. They're the same regardless of how long they've been in service because of the Markov property. So therefore, the time from the arrival epoch of the test customer until the first departure is the minimum of the S independent identical exponential service times that are in progress when he arrives. And we know that the minimum of S exponentials that are identical is S times the is exponential again with rate S times the original rate. So if, let's say that mu is equal to 1 over tau. Tau is the average service time, so mu is the average service rate. So that means that the time from 0 until the first service completion would be exponentially distributed, and its rate would be S mu. So from here to here is exponentially distributed with rate S mu. Everybody see that? Let me repeat that. The customers in service have exponential service times. So when a test customer arrives, the remaining service times of each of the customers is independent of how long they've already been there because of the Markov property, and is exponentially distributed with rate mu. The time until the first service completion is the minimum of those S exponential variables, and we proved in class that the minimum of S independent identical exponential variables was also exponential with a rate equal to S times the original rate. So if mu is the service completion rate per server, then S mu is the service completion rate for the S servers working together in parallel. So that means that the time from arrival of the test customer to first service completion is exponentially distributed with parameter S mu. Okay, now what happens? Well, the first service completion occurs, and this guy moves into service. His service starts from the beginning, everybody else's continues, but by the Markov property, those are all the same, and is independent of the past. So therefore, the time from this service completion until that service completion is also exponentially distributed, independent of the previous one, and with the same parameter S mu. And the same for the time between him, and so forth. So what we see is, as long as all the servers are constantly busy, then the output process is represented by these arrows, in which the times between arrows are IID independent exponential, each with parameter or rate S mu. So what do we know about a process in which the times between events, the times between these arrows, are IID exponential? What kind of process is that? It's a Poisson process. So that means that the distribution of the number of arrows in a fixed time has the Poisson distribution, and its parameter is the rate, or S mu. So if the length of time is t, the probability that there are exactly I departures in the interval of length t is S mu t to the I over I factorial e to the minus S mu t. Okay, so FIFO makes that work. That is, we must have exponential service times here, because it's the exponential service times that makes the inter-departure times IID exponential. And if we have FIFO service, then we know that the length of time this guy waits depends exactly on the number of departures that occur of the customers in front of him. So the probability that he will wait longer than t if he finds all servers busy and a queue of length j is the probability that during this interval of length t, exactly I customers depart where I is less than or equal to j. And the probability that exactly I customers depart is given by the Poisson probability, because if the times between departures are exponential, then the number of departures in the fixed time is Poisson. We proved that those two facts imply each other. That's a Poisson process. So therefore, we have this answer. So now the rest is arithmetic, because now what I have to do is I have to take this, put it in here, and sum. Okay, so let me do that. It's probably worth doing. I guess I can erase this. So it looks like it's formidable because you have this double sum, but actually it's easy if you write everything out. Okay, so what I have here now is that the probability of weighting greater than t is equal to, well, first of all, we'll have the Erlang C value. That was this piece right here. And then I'll take out my 1 minus rho. And then I have the summation as j runs from 0 to infinity of rho to the j. That's this term. And then I have the summation as I runs from 0 to j. And then I have this s mu t. Well, to simplify my writing, I'm just going to call s mu t equal to x. So for the moment, I'll just replace that by x to the I over I factorial. And then I have the exponential, which doesn't affect anything, so I'll put that over here, e to the minus s mu t. Let me rewrite this. This is a 1 minus rho, e to the minus s mu t. So all I got to worry about is this sum. Okay, now, if you're stupid, what you do, slow, I put it that way, what you do is instead of doing something clever, you just write everything out. That's really the easiest thing to do in this case. So let's see. When j is equal to 0, I have rho to the 0. And then I have the sum from 0 to 0. So that's going to give me x to the 0 over 0 factorial. So that's the term when j is equal to 0. When j is equal to 1, I'm going to get rho to the 1. And then I have in here two terms. When I is equal to 0, I'm going to get x to the 0 over 0 factorial. And then the next term is going to be rho to the 1. And now I have I is equal to 1, so I'm going to get x to the 1 over 1 factorial. And now it's obvious how the pattern's going to go. The next one's going to be rho squared x to the 0 over 0 factorial, rho squared x to the 1 over 1 factorial, rho squared x to the 2 over 2 factorial. I'll do one more row here. Rho cubed x to the 0 over 0 factorial, rho cubed x to the 1 over 1 factorial, rho cubed x to the 2 over 2 factorial, rho cubed x to the 3, rho cubed x to the 3 over 3 factorial. Okay, now look at the first diagonal. Okay, so we're going to look at all of these terms. Of course, this goes on forever. It's all of the form. I could take the rho and combine it with the x because the power is the same. So everything is of the form rho x to the 0 over 0 factorial, rho x to the 1 over 1 factorial, rho x to the 2 over 2 factorial, and so forth. So that, in fact, is the Maclaurin series expansion of e to the rho x. Right? Everybody buy that? Okay, now let's look at the next diagonal. Here I have the same as this, except that I have an extra row. If I factored out a row, then the exponent of the row would be the same as the exponent of the x. So with the row factored out, that means that that second diagonal is rho e to the rho x. And of course, then the third one, the third diagonal, is going to be rho squared e to the rho x. And so on. So when I get all done, the e to the rho x factors out. So I'm going to get e to the rho x times 1 plus rho squared and so forth. But of course, rho is a positive number less than 1. It's the server utilization. So assuming that there is an equilibrium distribution, rho is less than 1, which means that thing sums to 1 over 1 minus rho, geometric series. So this 1 over 1 minus rho cancels with that 1 minus rho. And this e to the rho x is e to the rho s mu t, because that's what x was. I don't know if I wrote that down, but when I went from, where is it? Okay, I erased. When I went from here to here, what I did was I simply said, let s mu t equal x to make everything simpler. So what does that mean? That means that after I do the cancellation, cancel out that 1 minus rho with that, and combine this with this, what I have is the Erlang C times e to the minus s mu t, e to the minus rho s mu t, e to the plus rho s mu t, which is e to the 1 minus rho s mu t. Okay, let me erase this stuff here. Can I erase this arithmetic? All right, so by this double sum is then really easy, because all it turns out to be is just that, with two terms that cancel that, with a term that cancels that. And this is my answer. The probability of waiting longer than t is the Erlang C times e to the minus 1 minus rho s mu t. This is very simple. Very simple and very neat. Notice, of course, that this piece is the probability of waiting time greater than 0. So therefore, that piece must be the probability of waiting greater than t, given that the waiting time is greater than 0. So that's interesting in itself. This piece is independent of the Q discipline, and this piece depends on the fact that I have FIFO service. If I didn't have FIFO service, then it would be, in general, much more complicated to figure out this thing right here. Now, what does this say? This says that I'll write it out. It says that the conditional probability of waiting greater than t, given that you wait greater than 0, in other words, the conditional distribution of w apparently is exponential, e to the minus 1 minus rho s mu t. Right? Because it's of the form e to the minus something. So that means that there's no memory in this variable. That means that if I arrive at a queue, in this kind of queuing model, and I have to wait, I find that all servers are busy, then if I have no information as to how long the queue is, if all I know is that I have to wait and I can't see what's going on, then the length of time that I have already waited, or no matter how long I wait, the future waiting time is independent of the length of time I've already waited. And this is not an assumption, this is a conclusion. So this explains life to me, because this is why I like this subject, is that they're the great mysteries of life, and this explains one of them. This is the famous restaurant theorem. Okay, in the restaurant theorem, what happens is you go to a restaurant, fancy restaurant, and you go up to the maitre d', and you say, how long do I have to wait? And he looks at the list, and he says, 15 minutes. And you say, okay, 15 minutes, thank you. He says, go wait in the bar. I'll call you when you're ready, when we're ready. So you go wait in the bar, and then 15 minutes are up, so you come back and you say to the maitre d', how much time do I have to wait? And he looks at the list and he says, 15 minutes. And you think he's putting you on, but of course he isn't putting you on, because this says that no matter how long you've waited, the length of time that remains is independent of what has already happened. Okay, so now you know why you always wait longer than you think you should wait at a restaurant with a maitre d'. So what else could you ask for in a subject like this? Who cares whether you can engineer telecommunications networks? If you can understand the important things in life, then you're in. Okay, so this thing is exponentially distributed. And we're out of time now, but in 10 minutes we'll start again, and I'll continue where I left off.